Right, well, wow, a superb turnout on the bleak midwinter. So thank you very much for coming along tonight. We've just got a few notices to start off with. So there we are, before we move on to page 4. So our previous institute lecture was on the 14th of November. I think we had a decent public turnout for that one. From what I've heard, everyone said it was an absolutely fantastic talk. So many thanks to Neil Young from Teesworks. A number of questions were asked, both thanks to Steve Martin and closing remarks as well. So we can take that as a record meeting. Moving on, our January Institute lecture. I think we've just about got everything sorted for the rest of the year, so please do check all of our channels and Eventbrite, etc. And our January Institute lecture will be joined with the local regional group of the Geological Society of London, and this is given by Dr. Nick Gardner, who has recently been theme lead at the Geological Society on critical metals. He's currently based up at St Andrews. It's a really interesting career, and of course all these things are pretty nifty, and I'm not sure that that's going to be some form of alkaline complex in Namibia, and I'm sure he'll be talking to you about. Of course, it's great to see so many people here. If you don't already follow us, there's the usual range of channels where you can keep up to date with all our events, etc. But of course, on what do we have on offer? Lectures such as these. We try and have at least one conference a year on various timely topics. The annual dinner, which is probably going to be late spring, early summer at this rate, but we're hoping to have a really large event for that one. Various social events, and of course the occasional field trip as well. So that pictures when we went off to find that giant millipede in Northumberland. Of course, the best way to keep up to date and also support our work is through membership. There's plenty on offer for all various levels of members. Lots of invitations to our wide and varied lecture series. Of course, also we try and put on a chartership event each year as well, and try to develop more professional events. Various other bits and bobs, and of course the opportunity to help us out via committees, etc. So don't forget, do please go and visit mininginstitute.org/membership, and you can find out more information, or indeed talk to us here. So please don't leave without a membership form. But now we shall move on to the topic of tonight's lecture, which is given by Professor David Manning of the University of Newcastle. David is a professor of soil science at Newcastle University. He's a chartered geologist and was president of the Geological Society of London from 2014 to 2016. He has worked closely with the minerals industry throughout his career and has had a special interest in the interface between geology and biology. He currently serves on the British Geological Survey Science Advisory Committee and worked closely on the construction phase of the UK Geoenergy Observatories. Currently, his research focuses on the use of rocks as alternative sources of crop nutrients, as well as of CO2 removal, with collaborations in Brazil and Thailand. So, I'll skip the abstract. I'm sure I can do that. All I'll add is he's also a fantastic external examiner. So if you're ever in need of someone to look at a terrible thesis, please do phone up David. Yes, so I'll hand over to David now, and we'll just get the IT working as well quickly for you.
That's okay now, is it? Yeah, so good. Yeah. Excellent. Well, thank you very much, Andrew, for that kind introduction, and thank you for the opportunity to speak to the audience here tonight. I'm going to talk about something which is actually quite close to my heart, which is quarrying, and that's coming from an academic standpoint, but of course it was having access and being able to look into the local quarry which got me interested in geology in the first place. So going back a very, very long time, and going back down memory lane, talking about Ratcliffe-on-Soar Power Station is very close to my heart as well, because I spent many an hour in a garden able to see it on the horizon. So a very interesting aspect of of my background as far as I'm concerned. So I'm going to look at what quarrying can do for the net zero world, and I'm conscious that a lot of quarrying activities relating to net zero relate to how can we reduce the carbon cost of quarrying as an industry, but there's more to it than that. So let me just move on. I'll just... First glitch, which you were having a problem with this as well, weren't you? Yeah, so...
Does that work?
Oh yeah, there we are. That's okay. Yeah, so I'm going to talk about carbon sequestration, so taking carbon dioxide out of the atmosphere, and how the quarrying industry can contribute to this through the topic of what we call enhanced weathering. Some of you may have come across enhanced weathering. Please forgive me for going over some of the ground behind this, because in this talk I'm going to explain a bit about why we need to do this in the first place, a bit of the scientific background to rock weathering and how it takes CO2 out of the atmosphere, to look at the role of silicate minerals in doing this, and then sources of the appropriate rocks for the task, and thinking about quarrying in this context. As you all know, we have a climate emergency, and it's perhaps easy to declare a climate emergency. It's much harder to do something about it and to magic it away. It won't go away of its own accord. We actually have to do something to deal with the climate emergency. So with that in mind, let's see where I have to send this thing to. The same issue again with I'm moving forward. Yeah. Too many keys to press. Yeah, it's okay. So we've got that going on that key there now.
Oh no! Oh. There we are.
What did you press?
For the benefit of viewers at home.
Yeah.
So as long as the cursor is here, then we should be able to
use the arrows. Okay, right. Excellent. So thinking about climate change then, we know we're talking about greenhouse gas emissions, and we know with this that we are looking at the issue in the graph here where atmospheric CO2 is rising, and similarly annual emissions are rising as well when we're talking about CO2. And we mustn't forget methane and nitrogen species. The IPCC has been modelling this, as we, again, are all familiar. And, of course, the models and the predictions are pretty dismal in the sense that we can see CO2 levels rising from about 400 ppm at the present time as we project forward in the graphic on the right. We can see this going, whoops, and that's my fault. Pressing the wrong button, I've got too many buttons. We can see in this part of the graph here, we've got the amounts rising where we're heading potentially for temperature rises of 3 to 6 degrees greater than what we have now in what we might call a very high emissions scenario. With very low emissions scenarios, we might stay between 1 and 2 degrees higher. We're very unlikely, I think, to reach those. So we have to change as members of the public. We have to think about how we can reduce our emissions individually, how we can move away from a consumer society which depends on the use of fossil fuels. That's one way of approaching this. The other side of the coin is that we collectively as a society have to remove atmospheric CO2 at scale. So we're doing that on a scale which is going to compensate for the use of fossil fuels in areas where it cannot be replaced. So at the moment we've got a heck of a long way to go before we can stop using fossil fuels as raw materials for manufacture of cement, of steel, as we heard from Andrew's talk earlier, and indeed from nitrogen fertilizers. And we must remember that the nitrogen fertilizers that enable us to sustain a world population of 8 billion people depend on methane as a raw material to make that ammonia that goes into those fertilizers. And it's this inertia in the transition to the non-carbon energy sources which are there as a real problem for us, because it's going to take decades for us to be able to move away completely from fossil fuels. There are ways and means of doing this, and the Royal Society kicked off this whole area of work in 2018 by setting the scene and setting out what some of the options were. And the IPCC has gone beyond that. So the IPCC has a taxonomy of CO2 removal with various methods which can be used, going from left to right, where we have land-based biological on the left here, going across to ocean-based on the right. We've got geochemical in the middle and chemical with direct air capture in the middle there. just in that point there. So with these, you can see that we're starting off with the obvious ones of afforestation, of putting trees in. We've got soil carbon sequestration, how we can increase the amount of carbon that's in a soil. We've got biochar as a particularly refractory and stable form of carbon that can go into the soil and contribute to fertility, but can also be used to dispose of wastes from forestry, residues from forestry. We've got bioenergy with carbon capture and storage, which is still putting CO2 into the atmosphere, but depending on capture of that CO2 by methods which include those that are featured in direct air carbon capture and storage, which use chemical processes to take CO2 out of the atmosphere. Enhanced weathering uses silicate rocks. There's not a lot said about it in this IPCC report because there isn't a lot that was on the table at the time they're putting this together. There'll be much more there now. And then as we get to the coast, we've got peatlands and coastal wetlands that we can restore. We've got blue carbon, where we manage carbon in the ocean. We can enhance ocean alkalinity, and that is contributed to by enhanced rock weathering through silicate rocks going to the ocean, and then ocean fertilization. And you can see that there's a very wide range of choices, and we'll probably need all of them. But when we think about it, forestation is not permanent. Forests grow and then they die, or they may get burnt down. When we think about soil carbon, that is equally temporary in the sense that if we have a ploughing-based system, then the soil carbon is oxidized as a consequence of ploughing, so it turns over. As indeed, you know, when you put compost on your garden, you have to keep putting compost in every year. Biochar is not yet at scale. I think there's only one plant in the UK that actually is able to manufacture biochar on the scale of tons and tens of tons. And similarly, bioenergy with carbon capture and storage. Again, that's got a long way to go to get to the scale that we require. With direct air carbon capture and storage, some very, very clever machinery and equipment is needed for this and has been invented and can be used for it. It uses a lot of energy, it uses a lot of resources. It's got, again, a long way to go before it can be done at scale. Enhanced weathering, enhanced rock weathering is growing remarkably rapidly. This is an industry which has kicked off since COP26 in Glasgow, and it is a bit reminiscent of the time when the oil industry was kicking off. When you look at how people are being employed in that sector, we can't hire postdocs to do this type of work now because they're all being hired by enhanced rock weathering companies and being paid a lot more than we can pay. So we'll look at that in a bit more detail as we go through the talk. With the peatland and coastal and the blue carbon aspects, it's vulnerable to climate change in itself. And then with ocean-based methods, what worries me about them is that they're impossible to reverse. The ocean is a large and complex system, and if we, as we know with all the plastics going into the ocean, we can't put that right easily. We can't meddle with the ocean and then come back to it and put things back to as they were. So I'm going to focus on soil-based CO2 removal, and here we're looking at nature-based solutions. We've got very low energy inputs for these to work, and we're working with nature, letting nature do all the work. And we have to remember that people have been farming soils for over 10,000 years, and we've learned a heck of a lot about how to manage soils, how we can make a mess of it, but we know how to put it right. So at least we've got that practice and that track record. COP21, the Paris COP in 2015, committed to 1.5 degrees increase in global temperatures and emphasised soil organic matter as one way of doing this. But it didn't mention soil carbonate, the inorganic carbon that you can get in soils, which is a permanent sink for carbon. And that's something which we want to focus on, because when we look at the carbon cycle, we can see beautiful diagrams like this that the IPCC have produced, and we can see that the focus here is on organic carbon and the biological carbon process. But what's interesting is when we look at the stock of carbon in the atmosphere, it's about 730 gigatons, and the churn, if you like, through soils, the vegetation and soils, is churning over 120 gigatons per year. So there's an elephant in this room, and that is that it only takes 6 years for all the carbon in the soil, the plant-soil system as a coupled system, to pass through the atmosphere. So if we want to make a difference to atmospheric CO2, if we can intercept carbon in the plant-soil system, then we can do something rapidly. And that's something which is very, very attractive. So the key to this lies in taking that carbon that's in that organic and that biological carbon cycle out of the biological carbon cycle. They're those highlighted, those figures which are the elephant in the room. And the question then is, how do we take carbon out of that biological carbon cycle? And that's where this rock weathering comes in. So, looking at the enhanced rock weathering agenda, it's growing rapidly. Let's have a look at it in detail and see what it involves. We know from the geological record that silicate rocks and their weathering are involved in controlling atmospheric CO2 compositions. It's long been known that there's a link between rock weathering and the amount of CO2 that's in the atmosphere. But we also know that as those rocks weather, they release nutrients that are required for the growth of crops. So they're releasing potassium and magnesium, which are key elements for crop growth, especially potassium, but also silicon, which is in grasses. It's the component of grasses that causes cows' teeth to wear down as silica in the grass structure. It's not a fertilizer material because it's deemed to be sufficiently in abundance, but if you're growing sugarcane in an oxysol in Brazil, then you need silica, you need to add silica to it. And of course, trace elements come from silicate rocks as well. So there's a wide range of contributions that they make when they weather. If we combine the two, we can have reduced dependency on chemical fertilizers, particularly in tropical soils, particularly in soils where you might be wanting to use organic production. And at the same time, you can remove atmospheric CO2. Well, the chemistry of this has a bottom line, a lot of slides that could have gone before this, that when silicate minerals weather, they release silica itself, which is electronically neutral, as SiOH4, but they also release these cations, calcium, magnesium, sodium, potassium, and so on. Now, those cations can't exist in the soil solution on their own. They have to have a counterbalancing anion, and that is bicarbonate. And you can see that on the side of any bottle of avian water, of any bottle of spring water that you might be drinking. You just look at the anions and the cations in the analysis printed on the side of the bottle, and you'll see bicarbonate is there. And we know that bicarbonate is the dominant anion in natural soil solutions and in shallow groundwater systems, in drinking water systems, derived from the weathering of these rocks. And hundreds of millions of people drink groundwater from these rocks, from aquifers based in silicate rocks, particularly basalts. And we also know that that bicarbonate comes from atmospheric CO2. And we know that it goes into the soils through photosynthesis. The plants are a pump. They're taking carbon out of the atmosphere. They're pumping it through their roots into the soil, where the microbes make hay with the compounds that are exuded by the plants. The end product is CO2, which a proportion of which goes into bicarbonate in solution. And then when high pH soils are the type you get on heaps like the steel slags in concert, where you've got very high pH, or on demolition sites, where again you've got very high pH, chemical reaction adds to this. So silicate minerals then, they're formed at high temperature, and we're talking about the rock-forming minerals, as anyone who's studied geology will know. They're forming in volcanic systems, in igneous systems, at high temperatures and high pressures, and then they become unstable when they're at the Earth's surface, where they may be oxidized and where there's water, of course. We know empirically from soil scientists going back to 1938, in this particular case the Golditch reaction series, which shows very clearly that the minerals associated with high temperature igneous processes are very prone to weathering, and there's a sequence then of the least resistant, the ones which weather easiest, starting off with olivine and the calcium plagioclase anorthite, with quartz being the most resistant to weathering. Quartz won't weather. Quartz is what's left after everything else has weathered away. There's a scientific background to this which comes out of the thermodynamics of the reactions of these minerals when they do weather. You can see here these negative numbers, which are the free energies of reaction for the weathering reactions of these minerals, are most negative at the top of the diagram, least negative at the bottom. And because quartz, as SiO2, only reacts to give SiO2 effectively when it dissolves, then there's no number given for that. So it fits. The science that's more modern fits the observations of Golditch from so long ago. So these are the minerals that we're thinking about, olivine, pyroxene, and plagioclase, which go into basalt. So basalts would be our target rock for this, the rock which is most likely to weather. And the weathering rates are also important. So how quickly will these things decompose in a weathering environment. And fortunately, not only are they the most unstable minerals, but the olivine, pyroxene and plagioclase also weather quicker than the minerals that you might find in granite. So whereas you might have a nice source of granite somewhere and you think, well, I'd like to use that, it's actually not really starting in the best place for enhanced rock weathering. But basalts are the target that people are going for. As they release these cations, you can see they're coming out in different cations for different mineral species, calcium, magnesium, principally potassium from K feldspar and muscovite. And we're getting those cations going into solution. And if we have enough carbonate there, we know we can get carbonate minerals to precipitate. So we can get pedogenic carbonates, as they're called, carbonate minerals which precipitate out in the soils, like in this picture here, which shows one in Calgary. You can see a little beard on that pebble. That's calcium carbonate. And you can do clever stuff with the carbon and oxygen isotopes, the stable isotopes in that carbonate, to show that it's photosynthesis. And you can show which photosynthetic pathway it was that caused that to form. So it's a very, very well-known, well-established process. Right, what rocks can we use? Well, people like this on this farm in Cheshire are taking rock dust from quarries and spreading it in vehicles like this. They never throw anything away. But we can see the basalt that we're looking at is defined very, very carefully, very precisely by the International Union of Geological Sciences as lying on a particular diagram with silica on the x-axis, sodium and potassium on the y-axis, basalt falls there. And that is where we also would find dolerite and gabbro, the other basic rocks. We have to remember that basalt is volcanic, erupted and made it to the surface. Dolerite didn't quite make it to the surface, it was shallow intrusions, and gabbro would be the deep former magma chambers, but they're all chemically and mineralogically similar, and they're all suitable for this purpose. And on this diagram, we find that those rocks which contain nepheline are weathering fast as well. Nepheline is a mineral which weathers very quickly. There are some nepheline-bearing basalts in the Midland Valley of Scotland, but basalts more normally don't have nepheline in them. And the granitic rocks on the right of this diagram weather slowly. So, if we've got our rock dust, typical picture of rock dust in the top right here, we can calculate how much CO2 we can remove by one of two means. We can use a carbonation reaction, which would assume very simply that we're producing calcium carbonate, or we could use the enhanced rock weathering approach, where Phil Remforth, who was a former civil engineering student at Newcastle, now a lecturer in Heriot-Watt University, came up with this equation, which basically calculates out from the XRF analysis what the amount of CO2 is that can be removed. And by putting the numbers into an equation of this type, making some corrections with that, which is tied in with phosphorus in apatite or tied in with sulfur, then we come up with the answer that basalt can remove about 230 kilos of CO2 per tonne of rock. Now, when we look at how much we need to remove, we can look at company websites and we have statements like this. Our company has a target to remove 1 billion tonnes of CO2 by 2030, by the end of the current parliament, in other words. And that needs 4 billion tonnes of basalt. And it needs a workflow, and this is why they have to employ so many people, because this whole business of measuring how much CO2 is removed, reporting it in accordance with international standards, and verifying it in ways which allow payment by the people who are buying their carbon credits through this route, that is actually a very difficult task that requires a lot of clever people. Well, this is where it will come from. It will come from quarries, of course. That's where silicate rocks are produced. And this is a picture of Barrowsford Quarry, as some of you may know. And we think about how much rock we actually produce in this country. The figures for Great Britain are about 116, 120 million tonnes of crushed rock, and 140 if we include production in Northern Ireland. And Mandekan and Remforth, Mandekan being one of Phil Remforth's RAs, researchers, did a study where they reckoned using BritPits, the BGS database, they reckon that about 10% of what's produced is basaltic. So that's the starting point. Where will that all come from? And I apologise for the blurry nature of this figure. a version control issue, of course. They reckon that there are 68 active quarries in basic silicate rocks in Northern Ireland and the central belt of Scotland mainly. Some in the north of England, which we know very well, others in Wales and the Welsh borders and into that part of the West Midlands, a few in Cornwall. These are extracting about 14 to 15 million tonnes annually, and we need to think about the fines because we know that most of the product that's coming from these are going into the construction markets. What we're interested in for enhanced rock weathering is the 5 mil down, the fraction which is fine-grained, like in that earlier picture of the dust that I showed. And thinking about the efficiencies of crushing and the way in which fines are generated, we can reckon that about a quarter of that amount of annual production is the amount of fines that you would estimate to be removed, which has the potential to remove almost 1 million tonnes of CO2 per year, 850,000 tonnes. That's quite an interesting number. And we know that there are getting on for 500 million tonnes of permitted reserves. So the permitting process through the planning system in this country and in Northern Ireland and in Scotland gives us a chance to know well what the production is going to be. So if we think about a cumulative production by 2030, that's about maybe 20 million tonnes of fines. So we might have enough material produced under current production with no changes whatsoever, just making sure all those fines were sent to the enhanced rock weathering market, that we could remove 5 million tonnes of CO2. Well, is that worth it? So in 2030, the emissions target for the United Kingdom is that we should be emitting 300 million tonnes of CO2 equivalent, and in 2024 we're emitting about 400. So we've got to find a way of getting 100 million tonnes per year out of the atmosphere to compensate for that. And without any changes, we could see current quarrying accounting for a 5% of that 100 million tonnes over the next 5 years. So it has got potential to make a difference when you think it's being put into practice alongside other processes. And that's simply without making any changes at all to current quarrying practice. So what are the challenges that we face? And there are 4 challenges I want to talk about. I'm quite sure that you'll have other challenges that you can throw at me afterwards. But we've got the challenge of the rock. What is the rock itself? The composition of those fines that are going to be sold. The carbon cost of doing this. Is it a carbon expensive exercise? Is it a benefit in that respect? What about the permits and the permission system? And what about logistics? Well, if we go to Beresford, and I apologise, this is a photograph taken in 2007, so I don't think this is visible anymore, but you can see here we've got limestone and mudstone overlying dolerite. And that is an important point to bear in mind, that the dolerite that you might be taking out of a quarry is accompanied by other minerals as well. And you might be able to separate them out to some extent, but in a quarry, an active quarry, there'll always be something going through which won't have any negative effect in terms of the geotechnical properties of the material when they're going off for aggregate sale, but we need to be aware of it, and I'll show you shortly. When geologists get their hands on a rock to do the chemical analysis of the rock, they want something looking like this, a beautiful pure dolerite with nothing in the way of weathering or alteration there. And here you can see that it's been plotted in that diagram. It plots exactly in the basalt field, spot on. It's just what we want. So that's what we're after. And loss on ignition, 1.3%, so there's hardly any water or any volatiles in it. When we get to the fines, so here are the 5 mil down fraction, the quarry fines. Yes, they plot in exactly the same position, which is very, very nice. So we say, okay, we're going to be able to work with this. But look at that loss on ignition value, 4.9%. That, when we dig down, we can look into the evolution of water and CO2 in this. This is using a thermal analysis machine which measures these gas concentrations. And we can see that there's kaolinite in there and there's calcite in there. And that needs to be taken into account. So we know that we've got the mudstone in the quarry, and so that's probably working its way through the crusher. That's where the kaolinite's coming from. We've got calcite from limestone in the quarry. That's where that's coming from. If you were to stick those numbers for the quarry fines into the Remforth equation, you'd end up with a if it was uncorrected, you'd come up with 230. But if you were to take into account the amount of calcium that's tied into the calcite, you would end up with maybe 200 kilos of CO2 per tonne. So it knocks the CO2 potential down if you've got a high loss on ignition, and you need to know that. Looking at the carbon cost of quarry production is remarkably low. This is a study that we did using data from Brazil, but I mean, they use the same equipment, Metso equipment and other equipment that we have in the UK, and the quarries have the same driving forces. But it only takes 5.4 kilos of CO2 per tonne of rock to make the product on average. That's the same as the CO2 cost of 2 to 5 litres of milk, depending who you talk to. So it's a trivial amount of carbon in the manufacturing stage. And when you think about it, it's not surprising, because you've got to get the prices down. It's a very competitive industry for the construction aggregates that are sold. It's had to become extremely efficient. And one of the ways it can become extremely efficient is by reducing its energy costs as far as possible. And then, of course, and in this context, this was in Brazil, in Brazil they use green electricity. It's hydroelectricity. It's 90% of the electricity supplied to the grid. So it's something where you can say, actually, it's very, very low in Brazil. And we start to think about then the difficulties that are faced by transport as being dominant. In this paper, we concluded that you could move basalt in Brazil and the Brazilian highway system in São Paulo state, which isn't very different to the one we've got, although it's got fewer potholes. You can move it 1,000 kilometres by road and still have a benefit. You wouldn't be able to bring your vehicle back to base, but never mind. So 500 kilometres would be an upper working limit if that vehicle came back empty. So with enhanced rock weathering, the workflow here has 3 stages, and we need to think about this from the point of view of the CO2 emissions, because it's quite a complex task to work that out for these, because we've got the quarry, the mine, where once you've installed that plant, once you've built that plant, it's constant for many, many years, maybe with minor changes as time goes on. It's with a major capital expenditure that's involved, and as we've just seen, it has relatively low CO2 emissions. Then, for transport, we have thousands of destinations, potentially. Certainly, with some of the people we're working with in Brazil, they're talking about thousands of farms that they're sending material to. And each one of those needs its own carbon life cycle analysis. So you can imagine the expense of doing that. It's enormous. And this is where the high CO2 emissions are. So you also have to take into account the spreading logistics and the soil type and the crop. These are operational expenses which accumulate and make it an expensive thing to do. And then on the right here, we've got the process of weathering, the plants growing, the CO2 going to the soil solution. That involves geochemical modelling. It involves measurements to validate geochemical models. This is where you need to have the operational expenses of having a team of people able to do that. So the company Undo, which I'll mention later, has 15 scientists employed to do just this in this country, 15 scientists at postdoctoral level with commensurate salaries. So it's really quite a difficult problem from that point of view. And here we've got the IT emissions, because it's very computer heavy working out what these costs are. And there we are, 4.5 billion tonnes going to 1 billion tonnes of CO2 removed. So that's the sort of supply chain in terms of the rock. With the permission side of things, one of the points that is important to bear in mind there is that quarries are well known within the planning system in this country and in many other countries as well. So it's not as though we're coming along here with a new thing. We're coming along here with an existing activity which can be extended. And the way in which the permission system works is that if you are in this region, for example, the minerals planning people in the local authorities are looking at projected need, they're looking at where quarries might be needed, and there's an element of strategy in minerals planning, which is to make sure that there's going to be enough raw material available for the construction sector into the foreseeable future. And that's very much helping with getting enhanced rock weathering embedded. And we see things like new quarries. So this is the Kirk-Welpington quarry, where the decision was announced last month. When I talk to people about permissions being given for new quarries in other parts of the country, they're astounded that it's actually possible to do. And of course it is, when things are done properly. From the point of view of logistics, Then again, this is a map from Mohammed Khan and Phil Remforth. The quarries are all in the north and the west. They're in the wrong place for arable cropping in particular. The distance is getting redder, going up to 1,600 kilometres from some of the quarries down in the southeast. But of course, we have this problem of how do we supply aggregates to the southeast of this country anyway, and we can see a difference which aligns with the agriculture here, with quarries to the north and west of a hypothetical line, and wharves allowing sea transport and unloading into docks, feeding into the more populated and part of the southeast of the country where arable predominates over pasture. So, what about the opportunities here? Well, it's this company Undo, and I commend Undo's website to you to find out more about this, simply un-do.com. They are the ones who state this target of 1 billion tonnes, and they are motoring. They're moving really quickly to build this up to scale. And it's a fascinating website to have a look at to see how they're doing it. They're doing trials at our farms, Newcastle University farms, both Cockle Park and at Nafferton Farm, so we're getting to know them very, very well. But they face a challenge of where they're going to get 1 billion tonnes of rock annually. That's a cumulative total of 1 billion tonnes, I should say. It's not annual. That's a mistake in the slide. We're producing maybe 15 million tonnes of basalt in total, which is about 1.5% of what's needed. That's 15 million tonnes annually, so maybe we could get up to 10% of that 1 billion tonne target by the time we get to their 2030 deadline. So it's heading in the right direction. How can we increase it? Well, we might stray into additional rock types. We're looking at basalt as being important, but there are other rock types that are of interest. We could do something which we've tried to prevent and avoid. We could see fines production increasing. If fines have a value, below 5 mil has a value, then, especially if it's got customers, then we might want to be able to make more and sell it. We can see that with current quarrying permits, then there could be another argument here with the enhanced rock weathering destination for products to extend permits, and it might make it easier to work proposals through the planning system. Similarly, it might make it easier to come up with proposals for new quarries because there's a new focus on the destination of the products. And we could, as we do with so many other things, consider importing. And in this case, we would consider maybe importing from Norway, where coastal super quarries are much more common than they are in this country. So we have quarries like this, the Jelsa quarry near Stavanger, 12 million tonnes a year being produced of granodiorite. An enormous quarry, and they claim to be the largest quarry in Europe, but then when you Google it, you find lots of other quarries claim to be the largest in Europe, so there's a competition there. These guys are able to do things at scale, and they can load into bulk carriers and move them around to our wharves and take it to where we want it to go. So that's something which hasn't been looked at yet, the possibility of moving rock from Norway to the UK with enhanced rock weathering in mind. And I'd like to think about a missed opportunity, and the question is, could we have had a quarry of that size in this country? And could we be glad that we had a quarry of that size in this country because of the climate emergency? Well, if I may mention Margaret Thatcher's name in this place, she said some really good things about climate change. It is mankind and its activities which are changing the environment of our planet in damaging and dangerous ways. The problem of global climate change is one that affects us all, and action will only be effective if it is taken at the international level. That's what she said in 1989. So that was quite a remarkable thing to reflect upon, especially when we think about what happened afterwards. But afterwards, we had the Harris Super Quarry proposal, which started its story in 1991 with Redland, I believe, and then moved across to Lafarge at the end of this saga. The plan here was to mine 10 million tonnes per year of a rock called anorthosite. So that anorthite, which is right at the top of those weathering diagrams, was the mineral in this rock. And the plan was to produce 10 million tonnes a year, so maybe 2.5 million tonnes a year of fines. That quarry could remove 600,000 tonnes of CO2 annually, almost as much as the rest of the quarries on the mainland of Great Britain. It would have been a remarkable thing. But the problem is, of course, it didn't get permission. People don't want quarries. And so it's now in a conservation area. It's not going to happen. And, well, who knows what will happen to that if it was ever resurrected, but it's going to be an uphill struggle. The snag is, though, that people don't want quarries, but they do want quarry products, and they take them for granted. So we live in cities, by and large. Proportionately more and more of us are living in cities, and we rely on transport infrastructure to get us from one city to another. And that all depends on quarrying, as we know. We've got to have the quarry products to be able to build the cities and the transport infrastructure. People want safe food, and the process of enhanced rock weathering is reducing the need for chemical fertilizers. The fertilizer industry is not encouraging this, of course, but it is something which we can maybe see develop further over the years to come, that this will become more important. People want jobs. In rural areas in particular, there aren't that many jobs. People want jobs which are well-paid jobs, so they can afford to live there. And so quarrying helps to meet those needs as well. And then, what do people not want? Well, the consequences of climate change are what we want to avoid. Floods, that's the one that's perhaps in most people's mind at the moment. But we need to think about migration. When we think about Africa, 1 billion people in Africa at the start of this decade, 2 billion people in Africa at the end of this decade, where are they all going to get the food they need? Because Africa's soils can't feed that number of people. We'll see migration in this Parliament rocket as a consequence of migration from Africa, as people are looking for the means to live, not just a better life, but the means to live. Malaria. People are talking about malaria as a disease that's coming back in the UK now as climate is changing. We don't want malaria, the ague that afflicted East Anglia. So there's lots of things which go wrong, and you have to ask yourself, is it better to have a quarry, a set of quarries that can help you mitigate this, or are we going to put up with all these things that are going wrong? Because, of course, floods always happen to someone else, but they don't. When you talk to students, groups of students, there's always a student in the room who's been affected by flooding, and there may be people in this room who've been affected by flooding. It's going to get more and more common as time goes on. So how can we change quarrying to make it more acceptable? That's the challenge. And of course we have to have safety first, which is the bottom line. But how can we improve the visual appeal? Because often the complaints are on the grounds of visual appeal. And indeed, you can see old installations like this, which is Middleton Quarry, as some of you will recognise, by the Pennine Way. That would never get planning permission today to have something like that built. But it does have a certain attraction to people who like Gothic type of architecture and the Whitby Gothic sense, perhaps. How can we hide processing? When we think about what's being done with the Woodsmith mine in Whitby, with all of the headgear underground, so you can't see a thing at the surface, the transport underground taking its Teesside, much more valuable product, of course, but which justifies that much larger scale of production. But are there ways we could think about the mining itself in a quarry to give an alternative to benches? Because one of the things which is striking about the Harris Super Quarry are the images of a hillside replaced with benches. And yes, it does look like an eyesore. I like looking at things like that, but then I'm biased. Lots of people don't like looking at things like that. But how can we, are there ways in which we could design the quarries so that they take the shape of what they're going to look like after they've been completed? Are there other ways we could remove the rock without giving that very, very artificial appearance? So there's a lot to think about, but what I want you to go away with is the view, I hope I managed to convince you, that quarrying does have a vital role to play in helping this country achieve net zero and other countries in the world. There are significant challenges, and there's a lot of money coming in to help solve those challenges, certainly in the enhanced rock weathering industry. And the really important thing to remember here, of course, is that we're not starting from nowhere. Unlike many of the other ways that are being thought of for taking CO2 out of the atmosphere, here we have an established industry, and that industry is one where there are these new customers coming along who are wanting to buy 1 billion tonnes of rock. That's kind of interesting. And we have to reflect as well upon our responsibility as a society where we're, again, not going to have anyone solve this problem for us. All of us individually are going to have to help do something to work together to get rid of the problems of climate change. With that, I'll leave you with this view of a Brazilian quarry. So lots to be put right there. But thank you very much for your attention this evening.
very much, David. I think we're possibly quite lucky that David Douglas isn't here and didn't come for your jugular earlier. But yes, if we yeah, as well. Who's on mic duty? Before we.
I've got my
Super. Any questions for David? Wait, and say who you are and where you're from.
Hello there, it's Bill Toads, I'm from Workshop. I'm a mining engineer. I've given a talk here before. Oh, sorry. Hello there, I'm Bill Tonks. I'm a mining engineer, ventilation from Workshop. I've given a speech here, I enjoyed it very much. So every tonne of carbon dioxide that we capture in this rock, scattered all over our soil in the UK, do we get carbon credits paid from around the world?
Yes, that's the business model of companies like Undo. They will get the carbon credits, and they'll take those carbon credits for the inorganic carbon that's removed. And what they have to do to get paid is to prove that that CO2 has gone into the soil. It goes into the soil solution, and then it drains away, and their model is that it ends up in the ocean. So you can imagine proving that is actually quite hard, but that's why they employ so many people as scientists to do that. And for the farmer's point of view, the farmer wouldn't get that carbon credit, but the farmer would get carbon credit for inorganic carbon that's being built, for organic carbon that's being built up in the soil as soil organic matter, which is something which is much easier for a farmer to demonstrate because there are commercial labs like NRM which can measure that. But no farmer, no matter how big they are, James Dyson and the others would not be able to afford to pay for the validation of inorganic carbon credits.
Okay, and so would it, in general, would it be profitable, carbon credits versus the cost of the quarrying? Would it cover the cost of the quarrying?
Well, it would be, they'd be buying the fines at the market rate set by the quarrying company. So the quarrying companies would be the companies that would be looking to make that profitable, and they would be setting the prices appropriately. So the prices vary. I mean, we've seen early examples where those fines have been sold at the quarry gate for maybe £15, £20 a tonne, and that price has been fixed by the quarry who's wanted to sell them. That's just an example. The prices are very variable, and they'll depend on what sort of contracts are struck between these companies who want to buy them and the quarrying company. So the quarrying company will be making a profit because it will make sure it makes a profit. The enhanced rock weathering company will be making a profit on the basis of its planned sales of the carbon credits.
Thank you. And would this teach the world how to do it all the other countries around the world?
Yeah, it's interesting because the industry is developing with one or two leaders like Undo in each country. So we're collaborating with Brazil, where there's a company called InPlanet, but there are other companies active in Brazil. There are 3 or 4 at least in the United States, there's some in Canada, there's one in Kenya, which is particularly interesting. So it's growing, and the community is talking to each other. So that, as one entrepreneur put it to me, there's more than enough CO2 to go round, so we don't need to keep secrets, there's more than enough to go round.
Thank you.
Thank you.
Any other questions?
Chris Calver, retired electrical engineer, actually. Thank you. Very interesting talk indeed. Thinking more broadly, across places that want to still produce effectively carbon, oil, gas, and things like that, might there be places where there are suitable rocks in those countries where they can reduce their effect by doing that?
These rocks are very common worldwide, as you know. I mean, basalt's one of the commonest rocks that is on the Earth's surface. And so, yes, the answer has to be yes, there will be enough rocks. Whether there's enough on the scale, if we're thinking of what, for example, we might need to do to compensate some of the Middle Eastern countries for production, you'd have to have enormous amounts of quarrying, but you'd also have to have something that would work in those climate conditions, and that might be more difficult. Having said that, there's some really interesting projects going on in Oman, where they're injecting CO2 into the Oman ophiolite, and indeed one of the people who's running that business hails from Hexham. So there's a local link to that project as well, and that's something where they've been injecting CO2 deep into underground formations to take the CO2 out of the atmosphere. So yeah, there's some interesting things going on.
Norman Jackson from Seaton Sleuth. Very good talk, very interesting. Can I ask a very simple question? A ton of CO2, are there any checks on what actually a ton of CO2 is? I relate to this. Are the tons you're talking about imperial tons, or are the American tons? And the reason why I'm asking that is because there's so many people who used to talk about a ton of coal.
I know.
And it was a completely different figure to loads of people.
Oh, you're right.
We were selling tons of coal, which consisted of carbon, but also of stone, because the power stations. So it's important to me to know, I think all the figures that you are quoting are complete theory. And I think the world is being told all of these figures, and I can just try to imagine what a ton of carbon dioxide would look like.
Indeed. Yes, well, it's a metric ton, but you're right about this problem of which ton is it, because you see a lot of literature which is ambiguous, and that's a big problem. Are they talking about imperial tons? Are they talking about American tons? And very often it's American tons, which are completely different. So there is a problem of that. But it's something where you're working with the scale of atmospheric CO2, where in those initial diagrams I showed with the carbon cycle, they're talking about petagrams and things like that. It's easier to work with tons, and to think in terms of large numbers of tons is to think of large numbers of grams. And I think that it's the scale of the problem that is the key to this, that we're faced with a really, really big challenge. We've seen all those fossil fuels going into the atmosphere, and we've seen the CO2 rise to 400 ppm in the atmosphere at the present day, and we're looking at the consequences of that and having to live with them. So to take that back out again, we've got a shorter time to do it, because if we delay, there's going to be even worse problems to deal with. And we've got to compensate for over 150 years worth of burning of fossil fuels in maybe 15 years. And so that's why some of these figures are so large, I think, because we're giving ourselves very large targets that we've got to do something about.
Maybe we need the Newcastle ton of CO2.
Have you got that in the cellar here?
We probably should. Any other questions at all?
Alan Judd, retired geologist. David, how do you measure the rate of weathering? And does that vary between, for example, Iceland, where there's plenty of basalt, UK and Brazil?
Yeah, the measurement of the rate of weathering is based on lab measurements of the pure minerals, and there are directories which give you the numbers that you need for that and various models that you can use. And of course they ignore what actually happens in the field, where you've got biology present and where you've got microbes present. And there's certainly evidence that the surfaces of these little rock fragments get colonized by particular microbes which are there for a reason, and they're there to accelerate the weathering process so they can get the nutrients that they want. So there's still a huge amount that we don't know about how we can actually define those weathering rates. There's some very, very nice experiments that were done in Iceland, looking at water draining through mountains, comparing forested mountainsides with unforested mountainsides, and showing the effect of the vegetation on the CO2 that was coming through that weathering process. So there are some studies of that type that have been done on a large scale.
Anyone else? I suppose something comes to mind. How beneficial to farmers is all of this? And then, of course, there's that debate of, do you plough, and then that has an effect on various organic and inorganic carbon versus whatever's. I suppose you might wonder, how do you stop a crust formation in the field as well?
Well, you're typically applying 20 tonnes per hectare, which isn't enough to give you a crust. And so it's that much actually disappears really, really quickly because the worms take it into the soil, and it soon is no longer visible apart from the very large fragments which the worms can't pass through their guts. We did an experiment at Nafferton Farm where we had an improvement in yield for oats of 20 to 30%. And that
where will this the yield of oats increase this year?
Partly, but it was a bad year for that study. It was last year. It wasn't this immediate past year, the one before. But what that showed was that actually this application of rock dust really did help when plants were under stress, and so they were able to compensate. But we talked to, there's a farmer in Heaven on the Wall that we know uses rock dust, and we've asked him, why did he buy it? You know, because he's one of these people who's been buying it at the quarry gate and having 2 or 3 wagon loads delivered every year. He says 3 things. First of all, my biodiversity has gone up. Secondly, my cows are happier. And third, my vet bills have gone down, and it's the saving on the vet bills that has enabled him to be able to afford to buy the rock dust. So those are things we wouldn't normally think about, but they're there as a customer's observations.
I'll go on then.
This is going back many years. I remember seeing a television program when I actually had a television program, and they were spraying oil on the desert so that trees could be planted for a green solution. Might it be possible to add this style of, dare I say it, rock to the sand to help with CO2 being taken from the atmosphere?
Yeah, it certainly could. We do experiments if we want to show how effective this rock dust is, or a rock dust is, in providing plants with nutrients. We do an experiment where we take ultra-pure quartz sand. We go to the Loch Alleen quartz deposit there. We buy from them. It's not cheap. And we use that quartz sand because it's got nothing else in it, absolutely nothing else in it. And we can see fantastic results. It shows up in 12 weeks, just in the right time period for a student project, that you can get the benefits from the weathering of that material.
Brilliant. Oh, yes.
Hello, David.
Hi.
Janie Vanisky from Wardell Armstrong. I'm a chartered mineral surveyor, and I look after lots of quarries that have got lots of fines and dust that they can't shift, which is perhaps a separate issue. But perhaps being slightly mischievous, one of the biggest complaints and issues we have when we're looking at quarries is dust. You're now talking about taking this material and spreading it on agricultural fields.
Yeah.
How do you think that environmental issue is going to be considered?
So the people who spread dust to soils in agriculture are very familiar with this because, of course, they know how to spread lime, which has exactly the same problems of dust. And what they're more concerned about is that they don't want the dust they're spreading on their land to be blown onto their neighbour's land, and so give them something for nothing. So they choose the timing very carefully, and they moisten the material before spreading. So they are experienced in ways of reducing and mitigating the dust problem, as are the quarries.
Lovely. Well, if we don't have anything else, then in that case, I think we shall move over to the vote of thanks. David Morris. I think for the recording, yes, I'm afraid.
Right, okay. All right. Professor Manning, that was fascinating. We heard during the AGM Andrew talk about the closure of Ratcliffe, the last coal-fired power station in the UK. We've had other lectures here talking about offshore wind and the changes, a sweep of 90 foot creating 0.2 megawatts, and now we're talking about 500 foot sweeps creating 17 megawatts, and now we're talking about removal of CO2 by ERW. And the interesting thing that I picked up on was to reduce the impact, we can't do it all in one go. We have to do it in stages because we can't simply stop the use of fossil fuels. And I thought that was music to our ears, because very often we're talking about stopping the use of fossil fuels, and it's going to take time, and we need to implement measures in between now and then to do that. And this is clearly one of those measures. So absolutely fascinating. And I think you'll probably all agree with the conclusion that Professor Manning is asking, the question he's asking, does quarrying have a vital role to play in achieving net zero? And I think we can all agree that it certainly does. So with that, I'd like you all to thank Professor Manning in the normal manner. Thank you very much. That was absolutely superb. Thank you.
Thank you.
Right, well, unless there's anything, unless Steve, there's anything else you need to find.
Oh, yes, there is.
Is there?
Please, can everyone who's coming here tonight make sure to sign the book and the paperwork. There is a slightly remuneration for the North of England Institute for doing so. I'd be very grateful if you could remember to do that. And other than that, it's down to you.
No, I forgot to mention the fire exits and stuff.
Oh.
And finding people for phones. I'm sorry,
Yeah,
you carry these lectures so well and turn up and make it out of it. Well, brilliant. Thank you very much for everyone for coming along. Our next lecture is, of course, on the 23rd of January. And that'll be, again, sort of metalliferous mining and all sorts of critical metal deposits, so that'll be good fun.